This video is the first video for Chapter 19, Chemical Thermodynamics. This is actually a continuation of IB topic 5, in which we covered enthalpy or delta H, and our Born-Haber cycles, etc. So those of you that are testing HL will see this kind of material on your exams in May. But everybody is going to test on this in class. Now, some of this you've heard of already, and some of this information will be new. When we talk about thermodynamics, we are talking about how heat is affecting a chemical reaction. And there are three quantities that we are going to associate with thermodynamics. The first is delta H, which you've already heard of. And we know that if delta H is negative, the reaction is exothermic. And if delta H is positive, the reaction is endothermic. And you guys will hopefully remember that back in Chapter 5, we were able to find the delta H of any reaction as long as we had access to the individual enthalpies of formation of each of the compounds or elements in the reaction. So we were taking the number of moles of the delta H's for the products, and then we subtracted the sum of all the delta H's of the reactants. And we did that again back in Chapter 5. So if you've forgotten how to do that, it might not hurt to look back at Chapter 5. Now the two new quantities that we're going to talk about are S and G. S stands for entropy. And entropy is a measure of disorder. We're going to talk about that in a little bit. So entropy can either increase, which means we're becoming more disordered, or it can decrease, which means we're becoming more ordered or less disordered. And then the last thermodynamic term is called delta G. And delta G will be able to tell us whether or not a reaction is going to be spontaneous or non-spontaneous. And that's something we need to talk about. So in this video, hopefully when you're finished with this, you'll have an idea, a little better idea of what spontaneity means, okay? So a spontaneous process occurs without any intervention from you. For example, if I have an egg in my hand and for some reason I let go of it, the spontaneous process is for it to fall because gravity pulls it towards the ground. It's going to fall, and when it hits the ground, it's going to crack and make a big mess. The egg is more disordered, messier, than it was before it fell. So the spontaneous process is occurring without intervention. The egg drops and makes a big mess. The non-spontaneous process would be the reverse. The egg is not going to somehow reassemble itself and fly back into my hand. Okay? And chemical processes can be spontaneous or non-spontaneous. If you think of taking salt and adding it to water, it is spontaneous that the salt will dissolve, separate into ions, and become more randomly arranged. Therefore, we're increasing the disorder. So you want to think of things in nature. Most everything in nature seeks to find an enthalpy or an energy level that is at lowest state. And things tend to seek disorder. Okay, and I always use this as you can use this as an excuse why your room isn't clean. Okay, you're too tired, you want to lay down, and the room is a mess because things naturally, in natural occurrences, it's the natural tendency for things is to go to disorder. I don't think you'll get away with it with your parents, but it's worth a try. Okay, now spontaneity can depend on temperature. So for example, if I take ice and I place it at a temperature that is greater than 0 degrees Celsius, the spontaneous process is for it to melt. Hopefully that makes sense. If ice is at a temperature above 0, it's going to melt. However, if it's at a temperature less than 0 degrees Celsius, it would not melt, so it would not be spontaneous. So sometimes reactions will depend on temperature, whether or not they're spontaneous or non-spontaneous. Now, the second part of this the new terminology is entropy. And again, like I said earlier, entropy has to do with disorder. So it's a thermodynamic term that reflects how disordered the particles in the system are. The greater the disorder, the larger the S value. S values can be positive or negative. And if you have a positive value, the disorder has been increased. So we would say entropy has increased. If your disorder, if the S value you calculate is negative, then you would say that the entropy is decreased. And you will look up these thermodynamic quantities just like you looked up delta H. It's in Appendix C of your textbook. Now, you're going to calculate the delta S of a reaction in the same way you calculated delta H. So remember, you're going to sum up your products first. And this N just means don't forget to multiply by the number of moles of each of those substances present. And then subtract from that the sum of all the S values for the reactants. Now, one thing I want to make sure you understand is that S has different units than delta H. The units of S are in joules per mole Kelvin. Delta H, you might remember, and these are standard values, so they occur at room temperature. Delta H was in kilojoules per mole. So it's just something to consider that the units are different. Now, I've got a practice problem for you guys to try. And although I know that you don't really carry your books with you back and forth to class, I think it would be to your benefit to actually look these values up in Appendix C, especially if I make a mistake. But hopefully you can see where they're coming from, okay? And it's really important when you look them up that you're on the right column, okay? So what we're going to do is calculate entropy change. And entropy is delta S. So to find the delta S for this particular reaction that I've given you, I need to first add up all the S values for the products. And then I'm going to add up all the S values for the reactants. And I'm going to subtract reactants from products. So it's easy to mess this up. Some of you might remember that with delta H. But I'm going to look up the value for H2O gas in Appendix C. And if you're looking this up, water is listed under oxygen. So the value for the water in the gas state is a positive 188.83 joules per mole K. And since there's only 1 mole of water formed, I'm going to multiply that by 1 mole. From that, I'm going to subtract the sum of the reactants. And the only reactant in this problem is water as a liquid. And I look up the value for that. That S value is 69.91 joules per mole K. And again, since I'm only forming 1 mole, I'll just multiply by 1. Now, using your calculators, you can get an answer of positive 118.92, and the label would be in joules per Kelvin. So that is our delta S value, and that is at standard conditions. Now, the second part of the question says, does the entropy increase or decrease? Well, seeing as this is a positive value there, underneath here, we would say that the entropy increases. So that's the mathematics of entropy. And then how do we think about this logically? These are the types of questions you might see more of on an IB exam. Generally, entropy will increase when some of these conditions occur. So if I take a solid, and you might remember that solids have particles that are well ordered, and if you get them to form either liquids or solutions, liquids and solutions have more randomly ordered particles. So the entropy would go up. It's going to become more disordered. If you take a liquid or a solid and make them form a gas, again, the particles are going to spread out farther and become more randomly arranged, so the entropy would increase. And then if you have the number of molecules, so here's an example of what I'm talking about. Let's say I have H2 plus O2 makes H2O. Now we know we have to balance this, and let's just assume all of these are in the gas phase. Okay, when I balance this, I need 2 H2Os and 2 H2s. Now, the number of molecules on my reactant side is 3, and the number of total molecules on my product side is 2. So 3 molecules moving around in space is more disordered than 2 are. So in this case, the entropy would decrease. If this were reversed, the entropy would increase. And then temperature. If temperature goes up, particles are going to move faster and more disorderly, and therefore the entropy would increase. So I have 2 IB test questions. Both of these multiple choice questions have appeared on IB exams, and I'm actually going to ask that you try them and come with those done to class, your best guess. What do you think the correct answers are? And I will go over them with you in class when we meet.